Hello everyone, welcome to our new lesson. So today we are going to discuss about very basic principles of strong acid and strong base titrations. So I'm Himasha Mahayagada. So let's take a look at basic principles of strong acid and strong base titrations. First of all, we are going to pay our attention on titration methods. Actually, what is this titration and what is the meaning of a titration method? Let's see. A titration method is based on determining the quantity of a reagent of non-concentration that is required to react completely with the analyte. So this is the meaning of a titration method. As we focus on acid-base titrations, we should talk about neutralization titrations also. So, neutralization titrations are widely used to determine the amounts of acids and bases. In addition, neutralization titrations can be used to monitor the progress of reactions that produce or consume hydrogen ions. Actually, these neutralization titrations depend on chemical reaction of the analyte with a standard reagent. These titrations depend on chemical reactions of the analyte with a standard reagent. There are several different acid-base titration. These different acid-base titrations are based on dissociation of acids and bases. So we have four main different acid-base titrations as strong acid, strong base titration, strong acid, weak base titrations, strong base, weak acid titration, and at last weak acid, weak base titrations. So today we are going to consider about strong acid and strong base titrations. So now let's talk about some strong acid and strong bases, because we have to know about strong acid and strong bases before move on to the strong acid strong base titration method. So here most common strong acids: hydrochloric acid or HCl, sulfuric acid H2SO4, nitric acid HNO3, and hydroiodic acid. And there are so many strong acids, and on these four are only few strong acids. And when we consider about most common strong bases, here I have listed only few strong bases. Mainly we use this sodium hydroxide, then here there's another one, potassium hydroxide and calcium hydroxide. Actually, these strong acids and strong bases are used as standard solutions in neutralization titrations, because these substances react more completely with analyte than do weak acids and weak bases. So as a result of that, they produce sharper endpoints. Because of that, strong acids and strong bases are used as standard solutions in neutralization titrations. So let's talk about strong acid and strong base titrations. Here, when we talk about strong acid and strong base titrations, first we have to know about the reaction. So as we are using strong acid, and this acid is strong, as this acid is really strong, so the H plus ions are completely reacted with OH minus ions which are coming from the strong base. So this H plus ion reacts with OH minus ion to give water molecules. So from the strong acid H plus is coming, and from the strong base OH minus is coming. When this OH minus react with H plus, then H2O or the water molecules are formed. So now as we are doing this titration, basically in laboratories we have to know or we have to get an idea about the titration setup also. So let's take a look at the titration setup for titrations. First, we have to have a burette like this. Then, usually we use a base in the burette, and here as we are using strong base, here we are using 0.10 m concentrated NaOH, and we need a titration flask. Here in our titration flask we are using our strong acid, that means 0.10 m concentrated HCl, 25 cubic centimeter. So actually in solutions of a strong acid that are more concentrated than 1 multiplied by 10 to the power minus 6 m, we can assume that the equilibrium concentration of H3O plus is equal to the analytical concentrations of acid. The same is true for OH minus concentration in solutions in strong bases also. Now we are going to do the titration. So base is in the burette and acid is in the titration flask. Now like this titration can happen. So this is the basically what happened in that happen when we are doing a titration. Now we have to know about the titration curves also. So now we are going to take a look at the titration curves. So when we consider about the plotting the titration curve for strong acid and strong base titration, we have to know about some specific points. So we are going to calculate theoretical values for these specific points. So we are going to titrate 25 cubic centimeter of 0.10 mHCl with 0.10 NaOH. First we should know about the net reaction. So the next reaction is, as I told you earlier, H3O plus is reacting with OS minus to give or to form water molecules. Here when we balance the equation, both sides of the equation, then we can have 2 water molecules. Now at the very beginning we have initial pH. So now we are going to consider and calculate this initial pH. Actually at the very beginning only the here we are using HCl 0.01 mHCl. So at the very beginning only the 0.10 mHCl to 25 cubic centimeter is remaining in the titration flask. So when we consider about the initial pH, it is totally based on the HCl or the concentration of HCl. So initial pH is equal to 1 as the concentration of HCl is 0.10 m. Because of that, initial pH is equal to 1. And next we have to calculate the pH at half equivalence point. This value like this. Here moles of acid minus moles of base. So we have to subtract moles of base from moles of acid. Then we should divide it by the total volume. By using this one, we can calculate the pH value at half equivalence point. So the thing is, moles of acid here, we know the concentration. To find the moles of acid, we have to use this one, concentration of acid, have to multiply by volume of acid. So we know the concentration of this acid, it's 0.1, and the volume of acid is, we have 25 cubic centimeter volume of acid in the flask. And when we find the moles of base, the concentration of base, we know it already, it is also 0.1, and so next we need the volume of base. Actually here the half of the HCl is already reacted with half of the moles of NaOH. So the half of the volume is equal to 12.5. So now we have to divide it by the total volume. So as the total volume is volume of the acid plus volume of the base, here volume of the acid is 25 and the volume of the base is 12.5. so when we add them at the 25 plus 12.5 together, we can get the total volume as 37.5. So by using that we can have the H plus concentration, and then by using that value we can find the pH, which is equal to 1.5. So pH at half equivalence point is equal to 1.5. Next we are going to talk about the pH at equivalence point. So at the equivalence point, no HCl or no NaOH exits, so the only species that supply ions is H2O. Because of that, pH is equal to 7 at the half equivalence point, as H plus ion concentration is equal to H minus ion concentration. And Next we have to think about the equivalence of pH after the equivalence point, but before that it's very important to find the one drop before equivalence point. It is 24.95 cubic centimeter volume. So when we do the calculation, we can get the pH as 4, and after the equivalence point, then there's no HCl, only the NaOH is remaining. So to find the pH after the equivalence point, we have to think about the OH minus concentration, not the H plus ion concentration. So when we consider about the moles of excess base, here one drop after the equivalence point, actually it is 25.0 cubic centimeter, because the one drop means from the burette means 0.05. So the concentration of base is, as you know, 0.1, and we have to multiply it by the volume of the base. Now the moles of excess base, because of that volume of the excess base we have to write it. So I'm writing it like this: 0.05. that means the one drop from the burette. Then we should divide it by the total volume, which is equal to volume of the acid plus volume of the base. So when we add them together, we can have the volume as 50.05. So now we can get the value for OH minus concentration. Then we know the OH minus concentration. So we can have the pOH, as you know, pOH equal plus pH equal to 14. We can find the pH as 10 here. Now we have done with the calculation. Let's look at the titration. Again, in the burette we have our base, and in the titration flask we have our acid. And now we are going to do the titration, and while doing the titration we are going to plot the titration curve also. So for the y-axis we have to add pH, and for the x-axis we have to add volume of NaOH. Let's do it. So now you can see initial pH is equal to 1, and here at half equivalence point pH is equal to 1.5, if you can remember the calculation. Then now we have done up to the one drop before equivalence point. That means this part, one drop before equivalence point, it is equal to 4. Now let's see, when we add another 2 excess drops, what will happen to the solution? Did you see that? So when we add another drop, that means at the equivalence point pH is going to be 7, and I have added 2 excess drop. That means now in this time we have 1 drop after the equivalence point also. If you can remember the calculation, 1 drop after the equivalence point, it should be 10. pH should be 10. So like that we can do the we can plot the titration curve also. Here when we add 1 drop after the equivalence point, you can see this pink color. It is because of the indicator. So normally acid base indicators are weak acid and weak bases. So best indicator should have the pKin value near to the equivalence point. So for this strong acid and strong base reaction, I have used phenolphthalein, which has a pH range between 8.3 to 10. Because it is the most common indicator that we can use. That's why in the base, with the base, it is giving pink color. That's why you can see pink color here. And we can use bromothymol blue as well, as it has a 6.2 to 7.6 pH range. Okay, so that's all about strong acid and strong bases. Please visit our website Life with Sense and do the quiz. There's a quiz. Do the quiz and check your knowledge. Thank you.